Dear students, next we are going to discuss about different types of electric fields. There are two types of electric field. They are uniform electric field and radial electric field, which is also called non-uniform electric field. We will be discussing about uniform electric field in detail in this lesson, and radial electric field will be discussing later in lesson 3. Uniform electric field. As we know, electric field is a vector quantity. A vector is having both magnitude and direction. If magnitude and direction of electric field remains the same everywhere, then such an electric field is what we call uniform electric field. Magnitude and direction of the electric field remains the same everywhere in this field. To represent a uniform electric field, we can use parallel and equidistant lines. Remember, those lines should be parallel and equidistant. And an example for such an electric field is the field between two parallel metal plates. Here you can see the representation. Two metal plates, they are equally charged but opposite sign. Direction is from left to the right, which is from positive to negative. And you can see one more representation here. Please note that these field lines are parallel and they make an angle 90 degree from the metal plate. I mean, the metal plate and field lines are perpendicular and it is from positive to negative, or it should be from higher potential to lower potential. That should be the direction of electric field lines. To calculate electric field strength in a uniform electric field, we can use the equation E is equal to V over D. Look at this diagram. This is the field between two parallel plates, which is representing a uniform electric field. Let V be the potential difference between these two plates and D is the distance between them. If so, E is equal to V over D. This is a very important equation for us, which will be given in the data sheet. The derivation of this equation is not important for us, so we can just ignore the derivation part. And from this equation, we can derive another unit for electric field, which is volt per meter. We have learned another unit for electric field strength, that is Newton per coulomb. Both units are same. You can try to figure it out. And remember, electric field, the magnitude of electric field strength remain the same everywhere in this electric field. Students, next we are going to discuss about two different graphs related to the uniform electric field. Here we have two parallel plates. So there is a uniform electric field between these two plates. Magnitude of the field and direction of the field also remains the same everywhere within this field. So if you plot electric field strength against distance, your graph would be a straight line parallel to the x-axis. We know that electric field strength E is equal to V over D. So if you plot potential difference against distance graph, the gradient of graph should give us electric field strength. Since field strength is a constant, your graph should be a straight line passing through the origin. Remember, the value of the electric field strength in a uniform electric field does not change. I have four different types of questions to discuss with you, which are usually asking for the exams. The first question is asking you to draw electric field pattern around this proton. Since proton is a positively charged particle, field lines are radially outward. So here is the diagram for you. Here I drew 4 field lines. If you come across such a question in the paper, 4 field lines are more than enough to score the full credit. You don't need to do more than 4. If you do more than 4 field lines, you will easily lose the symmetry of the diagram. And the other points to be noted when you draw such a field pattern is, don't forget to add the direction of the field lines. These field lines should touch the surface of the charged particle, and it should be perpendicular to the surface of the charged particle. Above all, try to maintain the symmetry of the drawing. Second question is to calculate electrostatic force on the electron in the hydrogen atom. We know that these electrons are revolving around the positively charged nucleus. So to calculate force between these two, or to calculate force on the electron, we can use Coulomb's law. Here is the equation for Coulomb's law. And charge of electron and charge of proton both are same. Proton it is positive, electron it is negative. And if you substitute the values, this would be the answer. And you get a minus symbol also. Here I forgot to add the minus symbol. That minus is representing that the direction of force on electron is attractive, or it is attracted towards the proton or the nucleus. In this question, liquid crystal displays are made from 2 parallel glass plates which are 10 micrometer apart. This diagram shows a clear explanation of the situation. The first question is asking you to calculate electric field strength between the plates. So there is a uniform electric field between the plates. To calculate electric field strength of a uniform electric field, we have to use E is equal to V over T, where V is the potential difference between the plates and T is the distance between them. And if you substitute, you get 1.5 times 10 to the power 5 Newton per Coulomb. And the second question is asking you explain what happens to the liquid crystal molecules. Remember, since the upper plate is connected to the positive terminal of the battery, that plate is positive and the bottom one is negative. These dipoles are placed in an electric field. So definitely the positive charges would be experiencing a force towards the negative plate and negative end of the dipole towards the positive. Because of this force, the molecule rotates and align with the direction of electric field. Dear students, in this question, an oil drop is suspended in a uniform electric field produced by 2 parallel metal plates. Distance between these 2 plates are 6 centimeters. In the first question, they are asking you to add lines to represent the electric field pattern between these 2 plates. As we know, this is a uniform electric field, so we need parallel and equidistant lines. In the second question, they are asking us to identify charge on this oil drop, whether it is positive or negative. As we know, this oil drop is suspended between these 2. Right now the oil drop is stationary. If the only force acting on this oil drop is its weight, it has to accelerate downwards. Still, if that oil drop remain at the same position, weight of it is balanced by some other force acting on this oil drop. Since it is placed in this electric field, the Force on this charged oil drop is nothing but the electrostatic force of attraction towards this positively charged upper plate. Since the upper plate is positive, the charge on this oil drop should be negative. Next, they are asking to draw a free body force diagram. As we have discussed just now, two forces acting on this oil drop are its weight and electrostatic force of attraction. Both forces are equal but acting in the opposite direction. So when you draw the free body diagram, length of these two arrows should be equal. Next question is asking you to calculate charge of the oil drop. To do this question, we have to use the concept of equilibrium. Charge is at equilibrium. So the electrostatic force and weight are equal. From the definition of electric field, E is equal to F over Q, or F is equal to QE. QE is equal to weight. The value of electric field is not given to us in this question. So we can use the equation E is equal to V over D to calculate the strength of the electric field. Or if you rearrange this equation, you will be getting Q is equal to W times D over V. By substituting the values, you get 9.59 times 10 to the power minus 19 coulombs. So this much excess negative charge is there on that oil drop. And next question is asking you how many excess electrons are there in order to achieve this much coulombs charge. To proceed with this question, we can use the information charge of one electron is equal to 1.6 times 10 to the power minus 19 coulombs. So 8 electrons can give 9.59 times 10 to the power minus 19. If you cross multiply, you get 5.99 electrons. If you round off that number, we can say there are 6 electrons. 6 excess electrons are there on the oil drop to get an excess negative charge. This is the diagram of an electron gun. As you can see in this diagram, there is a metal filament connected to a very high voltage power supply. There is a positively charged anode which is connected to a very high positive voltage. When the filament becomes hot, it starts to release electrons from it. This phenomenon is called thermionic emission. The emission of electrons by heating a metal is called thermionic emission. So these electrons create a beam and got attracted towards this anode, and it leaves the anode with a very high kinetic energy. In order to calculate this kinetic energy of electrons, we can use this equation. Work done by anode potential is equal to kinetic energy of electrons. This question is about an electron gun. In an electron gun, electrons are accelerated with the help of a positively charged metal plate. So here they are asking you, when electrons are fired from this gun, what would be the velocity of it? To do this kind of questions, we have to use this information. Work done by electric potential is equal to the kinetic energy of the electrons leaving the electron gun. That is, QV is equal to half mv square. This QV stands for work done. Work done is equal to kinetic energy. And how are we getting this equation? We have learned in AS level that from the definition of electric potential is equal to work done per unit charge, right? If you cross multiply, W is equal to, that's work done is equal to q times v. So if you multiply charge of the particle and the potential difference used to accelerate it, we get work done by this potential. So that's the reason why instead of this work done, here I am using qv. qv is equal to half mv square. So you have to take down this equation. So proceeding with this equation, qv is equal to half mv square, and rearranging the equation will give you v square is equal to 2qv over m, or v is equal to square root of 2 times charge of the electron times electric potential, which is 2.1 kilovolts, divided by m. M stands for mass of the electron. If you do the proper substitution, you get 2.72 times 10 to the power 7 meter per second. According to this question, electron is deflecting vertically upwards, right? So they are asking us to draw the field pattern between the lines. So to draw the field pattern, we should know charge on both plates. Charge of this particle is negative since it is an electron and it is deflecting upwards. So what should be the charge on the upper plate? It should be positive. So upper plate is positive and lower plate is negative. So your drawing would be like this. To score full credit for this question, we have to draw just 3 field lines only, and that could be drawn like how I am doing here, one at this end, one on the other end, and one exactly at the middle. If you do it like this, you won't lose the symmetry. And in one of the previous slides, I told you at the edge there will be a slight curvature for the field lines, right? But you can ignore it. If you do such a diagram for your final examination, you can score full credit. In the next part of the question, a potential difference 550 volt is applied across the plates of another deflection tube. The vertical separation of the plates is also given. Show that electrostatic force on an electron between the plates is about 2 times 10 to the power minus 15. So these are the given information. We know PD between the plates and distance between them. Calculate the force. F is equal to Q times E. Charge of the electron times electric field strength E is equal to V over D, which is in terms of potential difference and distance between the plates. Substituting into this equation gives 1.76 times 10 to the power minus 15 Newton. In the next part of the question, electron in the beam enter a region between the plates horizontally. Look, there's a region here between the plates. Electron is entering horizontally. Length of the plate is 10 centimeters. Speed of this electron is 2.2 times 10 to the power 7 meter per second. And they're asking you to calculate the vertical deflection, which means this is the original direction. It's being deflected upwards, and here this is the deflection, vertical deflection, which is h. So question is asking you to calculate this h. To calculate this vertical deflection, we can use one of the equations of motion, s equal to ut plus half at square in vertical direction. In vertical direction, initial velocity is equal to 0 as it is entering into this region horizontally. Now, we don't know the time taken to complete the path and acceleration of its journey also. So those two can be calculated separately. In horizontal direction, no force is acting on this electron. The direction of force acting on the electron is vertically upward. Hence, we can use equation velocity is equal to displacement over time in horizontal direction. Or if you rearrange it for time, we can write time is equal to displacement in horizontal direction divided by velocity in horizontal direction. Displacement traveled in horizontal direction is 10 centimeters and its velocity is 2.2 times 10 to power 7 meter per second. Substituting the values will give you 4.55 times 10 to power 9 seconds. That is, to complete the journey it takes 4.55 nanoseconds. Time taken to complete this horizontal path and this vertical deflection are equal. So we can use the same time for this calculation as well. Next, we have to calculate the acceleration. For that, we can use Newton's second law. F is equal to ma, or acceleration is equal to force over m. We have already calculated force acting on this electron, which is 1.76 times 10 to the power minus 19 divided by mass of the electron, which will give you 1.93 times 10 to the power 15 meter per second square. Substituting the value for time and acceleration in this equation will give you 1.98 times 10 to the power minus 2 meters. Since initial velocity in vertical direction is 0, the first term of the equation becomes 0. This is equal to 1.98 centimeters. These are the equations we have learned from this chapter so far. Coulomb's law, inverse square law concept. This is from the definition of electric field. Force per unit positive charge, E is equal to F over Q. By rearranging this equation, F is equal to QE. This equation can be used to calculate the force acting on a charged particle which is placed in an electric field. Using Newton's second law, we can write this F is equal to ma, which is equal to QE, or we got another equation for acceleration. A is equal to QE over m. Next is the equation for electric field. E is equal to V over D for a uniform electric field, where V is the potential difference between the plates and D is the distance between them. And by rearranging the same, we get V is equal to E times D. And these are the constants we have from this chapter. Coulomb's constant, charge of an electron, mass of an electron, mass of a proton, and the conversion between the units of energy, electron volt and joules. We have 2 follow-up activities as usual. Please submit both assignments on time. We will continue in lesson 3. Thank you for watching.